Hello there, 6th period. Okay, so this is the number 4 question from your 2014 B that we didn't quite finish. It reads, train A runs back and forth on an east-west section of railroad track. Train A's velocity, measured in meters per minute, is given by the differentiable function v sub a of t, where t is measured in minutes. Selected values for v sub a of t are given in the table above. Okay, so we've talked about this many times, but with free response problems, remember 15 minutes per problem on average. This particular problem here is a 4-part problem, so you're thinking we're spending a little under, right around 4 minutes per part potentially. Again, on average, you might not spend as much as 4 minutes on one part, but then spend a little bit more on another, that type of thing. But one of the first things you're going to do as you're reading, right, is to dissect it, to rewrite things, to define items or terms that you recognize, if nothing else to recognize kind of what's being described in the problem. So as I read this one, there's a couple of things that are highlighted to me, not many in this like opening section here, but a couple. I see that train A is east-west, right? So I'm already picturing my train A going sideways. Put a little A in there for train A, right? Kind of x-axis oriented here, right? Train A's velocity, I see I have units here, so I know if I'm measuring a distance of some sort, I'm in meters. Time of some sort, minutes. Velocity is meters per minute. Acceleration would be meters per minute squared. That type of thing, right? Okay. And then my table up here, I am going to make note, is velocity of A, right? Or the rate of change of A, the derivative of A. Okay, so here we go. Part A says, find the average acceleration of train A over the interval 2 to 8. Okay, this one here was worth 1 point this particular year, and it was for the average acceleration. So as we are solving this, okay, the formula for average acceleration technically is change in velocity. So we'll call it v of b minus v of a. So change in velocity over change in time. This was on the first packet that we did with our particle motion back in Unit 7. If you forgot that formula, you can derive that formula using average, right? We know what average is. Average is 1 over b minus a times the integral from a to b of whatever they ask you for the average of. In this case, this is average acceleration. And in this particular problem, my a is 2 and my b is 8. And so I know this is 1 over 8 minus 2 times the integral from 2 to 8 of acceleration. Okay, and so then if we're looking to take this antiderivative, this integral, the antiderivative of acceleration, the undoing of the derivative that got me acceleration, well, if you take the integral of acceleration, if you undo that derivative, you get velocity. Right? In this particular case, it's velocity of my train A. Right? That's that relationship. If I took the derivative of velocity, I get acceleration. So the antiderivative of acceleration would be velocity. And then we're going to plug in our upper. So we get v sub a of 8 minus, plug in our lower, v sub a of 2. And you see here we have that change in velocity over the change in time, which is what this 1/6 represents, right? I could write this as v sub a of 8 minus v sub a of 2 all over 6 if I wanted to. Okay? And so then your 1 point comes from actually plugging in numbers, right? And so my velocity at 8 is negative 120. Minus my velocity at 2, which was 100. Okay? And you could leave it there, or you could take it all the way. Negative 120 minus 100 is negative 220 times that 1/6, okay, which is negative 110. Yeah, I would just reduce. You could turn it into a decimal, I suppose. But again, with this being a non-calculator problem and being a free response problem, I would highly recommend leaving it here, right? You've plugged in numbers. That is something you could stick into your calculator. It would evaluate an answer for you, and so you are allowed to leave it there. This would earn you that point. In terms of units, while they didn't ask you for units, let's go ahead and talk about units just in case. If that were to show up on another problem, for example. Acceleration, so we're finding average acceleration, the middle acceleration, if you want to think of it that way. I mean, it's not perfectly middle, right? But the average kind of represents sort of that middle-ish number of the collection that has accumulated, right? So it's the middle-ish acceleration, but the key here is we're talking about acceleration, right? Well, acceleration's units are going to be meters per minute squared. Because again, your velocity was measures meters per minute, so acceleration would be meters per minute squared. Okay, so that would be a point. Okay, B. B reads, do the data in the table support the conclusion that train A's velocity is negative 100 meters per minute at some time t within the interval 5 to 8? Give a reason for your answer. Okay, so as I read this one, I'm thinking already, okay, so 5 to 8, I'm looking here, here's 5, here's 8, and I can see my velocities at 5 and 8. Okay, and it says, does that support the conclusion that train A's velocity has to be negative 100 at some point in that interval? Okay, this was worth 2 points, and the answer is, well, yeah, right, think about it. At t equals 5, at 5 minutes, my velocity of my train was 40 meters per minute. At time t equals 8 minutes, my velocity was negative 120 meters per minute. Well, to get from 40 down to negative 120, I had to cross through at some point negative 100, right? That's what lies in that interval, negative 100, right? So it was 2 points. 1 point was given for identifying that your velocity at 8 was less than negative 100, and negative 100 is less than your velocity at 5, at 40, right? AKA it's somewhere in between. The negative 100 is between 40 and negative 120, that type of thing. And then your second point was for your conclusion that yes, therefore, this does support the conclusion that train A's velocity is negative 100, and the reason, which they say to use IVT. Now a note, you don't have to specifically name IVT, name that theorem, as long as you describe the theorem. Right? This is the explanation that I wrote down. Yes, because velocity v sub a of t, which is a differentiable function, right? The fact that it's a differentiable function is what allows us to guarantee it. We talked about that in Unit 7. That's a phrase you're going to kind of want to have in your back pocket a lot of times when it comes to guaranteeing a point. Right? So yes, because v sub a of t, which is a differentiable function and therefore continuous, changes from 40 meters per minute to negative 120 meters per minute on the interval 5 to 8. By IVT, v sub a of t must pass through negative 100 meters per minute. Okay. Okay, part C. At time t equals 2, train A's position is 300 meters east of the origin station. Right, so I'm already thinking here 300 meters east, so I don't know, somewhere here. Here's train A, some distance from origin station that I know is 300 meters. Right, and this is at time t equals 2, so I'm going to go ahead and give this a position here. At t equals 2, I'm at that 300, right? And the train is moving to the east. Write an expression involving an integral that gives the position of train A in meters from the origin station at time t equals 12. So they're asking me here for what's the position at 12. Right? Use a trapezoidal sum with 3 subintervals indicated by the table to approximate the position of the train at time t equals 12. This one was worth 3 points. The first point was for your position expression. They ask us here to write an expression involving an integral that gives the position of train A in meters from the origin station. Okay? At time t equals 12. Okay, well, position, I know my desired position formula here is, let's go ahead and write it up here, x sub A plus the integral from A to B of your velocity. All right, this is again from Unit 7, desired position formula. X sub A plus the integral from A to B. So if I'm wanting to write an expression for at time t equals 12, and I put a little a here, actually I'm going to change it to a capital A so it matches my velocity. Because again, I know I'm talking about train A still. Right? So my position, my x sub A is the given position. In this case, I'm given that my train is located at 300. A is the given time of that given position, right? So at 300 meters, this was at time t equals 2, so my given time is 2. And then B is my desired time, the one I'm looking to find. And so in this particular case, I'm looking to find my position at t equals 12. And so 12's up here. Okay, and so this was 1 point. Straight from Unit 7, we did some of these. It showed up on your Unit 7 quest. Writing position, or desired position. Okay, second point is for using a trapezoidal sum. And we're told here that we are looking for 3 subintervals. Okay. And so as I'm looking at my integral from 2 to 12 and then looking at my table, well, 2 to 12, I have a very obvious 3 subintervals. 1, 2, 3. And so for my trapezoidal sum, I'm going to go 1/2 their change. So for my first subinterval, 2 to 5 is 3. And then both 140, which is 140. Second subinterval, 1/2 the change, 5 to 8 is 3. And both 40 and negative 120, which is negative 80. And then 1/2 the change, last subinterval, 8 to 12 is 4. And both negative 120 and negative 150, which makes negative 270. Okay? Just this trapezoidal piece, not even the 300 out front, just this trapezoidal sum piece was 1 point. Okay. Even if you hadn't been able to figure this out, right, you might have just looked at it and gone, okay, use a trapezoidal sum, 2 and 12. Okay, I'll use a trapezoidal sum, 2 to 12, right? Like that might have been how you landed on that trapezoidal sum piece. Okay, and then the third point is for the actual position at time t equals 12. Well, this trapezoidal sum piece is just the integral part of my position expression here. I was already 300 away from origin station, and so if you have this 300 in front of your trapezoidal sum, that's your third point. And the third point technically is for the whole value. If you leave it like this, your third point then is associated directly with the 300 essentially, because you already have your trapezoidal sum piece there. If you were to further simplify this, but again, I wouldn't recommend further simplifying it, but if you were to further simplify it, then the third point wouldn't really be associated with the 300 so much as it would be associated with the final answer. But again, if you make a mistake in your simplification, you've now lost that answer point. And so I wouldn't simplify. I mean, honestly, I might even recommend not making it, 140. I might make it 100 plus 40. Or rather than making it negative 80, make it 40 plus negative 120, right? If you think you might even just add those incorrectly. You don't even have to simplify this far, right? If you were to simplify all the way, this does work its way down to negative 150, which would be, this would mean we were west of our station, right? 150 meters west of origin station. At t equals 12. Right. And so again, if you were to simplify all the way down, then obviously your answer would be associated with that. Or your third point, I should say, would be associated with that. Oops, sorry about that. Okay. Okay, and then part D here. Part D, we are asked, or we are told, I should say, that there is this second train, B, that travels north from the origin station, right? So I'm already thinking here, just like I drew my little train A up here, train B, it's going north here. Go ahead and put a little B in there. Okay. At time t, velocity of train B is given by this function. So as opposed to velocity of A, which is my table, my derivative here, my first derivative for B is the equation. And at time t equals 2, the train is 400 meters north. So I'm given another little position here. Let's actually call this y since it's going north-south, up and down. So we'll call it y of 2 equals 400. Find the rate. So rate, as we've talked about many, many times at this point, this is derivative. So find the derivative in meters per minute, find the rate in meters per minute at which the distance between train A and B is changing at time t equals 2. Okay, so as soon as I read that, I'm like, distance between, I haven't really been given anything about distance between. I'm told that train A is east-west and train B is north-south, and I'm given some positions there. But I can't yet picture the distance between the two trains. And so this is, again, where if you aren't given the picture, you need to give yourself the picture, right? Train A, we know train A was east-west. And all of this revolves here around t equals 2. Well, I know some stuff about train A here at t equals 2. I was told that at t equals 2, train A's position is 300 meters. I know that its velocity, or its derivative, v sub a of 2, right? I know that its velocity at 2 was 100, right? So this is, again, I'm just writing down information I know. I don't yet know how it's going to come into play, but it's stuff I'm given at t equals 2, right? So this is train A here, and then I'm told train B is a north-south train. And again, I'm told some stuff about B as well at t equals 2. Well, B at t equals 2 was 400 meters away from the origin station, right? That was given right here. And I know what my velocity is of B at 2. You could actually calculate the velocity potentially, -5 2 squared, or times 2 squared plus 60 times 2 plus 25. Or you might just leave it in all of its unsimplified glory of -5 times 2 squared plus 60 times 2 plus 25. Right? And that's that one's derivative, first derivative, its velocity. Right? Okay, and so now I'm like, okay, well, so the distance between, well, that would be here, right? The distance between A and B. And then when I draw that in, I notice, oh, well, that makes a right triangle. And if this is train A and this is train B, well, this side of my right triangle, I'm going to call that C. Right? ABC. Right triangle here. Okay, well, and if this one's 300, 400, C has to be 500, a 3, 4, 5 triangle. If you didn't remember it was a 3, 4, 5 triangle, that's where you would want to use the Pythagorean theorem and actually calculate that C, right? Your A squared plus your B squared equals your C squared, right? But obviously it's going to save you time if you recognize the 3, 4, 5. Okay? And they're wanting me to find the rate, the derivative, right? My dc dt. Or if you wanted to keep it in kind of matching how this problem's been giving them, you might call this your velocity of C, potentially, right? Where C is not actually a train in this particular case. C is just the distance between the two trains, but right, still the velocity that distance is changing at, the rate, the derivative, right? That's what they're asking us to find. Okay, so you've got all that set up, right? And again, at this point, it might just be that you're writing anything you can think of related to this problem still. Okay, and so then you're sitting there with three points for this problem. The first 2 points come from the implicit differentiation of the distance relationship, aka taking the derivative of the formula we've got here, right? The implicit differentiation of our distance relationship. Well, with a right triangle, our formula is Pythagorean theorem. And we took a ton of these back in Unit 4b with our related rates. The derivative of a squared is 2a dA dt. Or again, you might call it v sub a. I don't know. Again, it would be what you would prefer. 2b dB dt equals 2c dc dt. And then you can plug stuff in that you know. A, we know, was 300. dA dt was 100, the rate of change, the velocity of A. B was 400. dB dt, again, you may or may not have simplified this. You might just have left it as -5 times 2 squared plus 60 times 2 plus 25. Okay. Equals your 2c, c was 500, and then the dc dt that we're trying to find. Your third point is for the answer, is for solving for that dc dt, which again, you don't have to do any simplification. This might just be dividing this 2 times 500 over underneath all the rest of that work. You'd have your 2 times 300 times 100 plus 2 times 400 times -5 times 2 squared plus 60 times 2 plus 25, all divided by 2 times 500. Let's put it in parentheses actually. Okay. And this would of course be meters per minute in terms of units. Right? Again, I wouldn't simplify any further. This gets you that answer. Right? If you were to simplify all the way, this would take us down to 160 meters per minute. Okay? And there you go.